Hi, I'm Cheuk. My Chinese name is Ting, but you can call me Cheuk. It's just like, when I moved to UK, now everybody call me Cheuk. I can tell you the story of how my name is so like messed up by the British, but that's the story for another time. I work for JetBrains. I'm working with the PyCharm team. So if you have any questions about PyCharm, or if you have complaints, then please come to find me. I would try my best to help you. Also, I call the Python GIL. I don't know, some of you call it GIL, some of you call it, I don't know what you call it, but I'll call it Python GIL in this talk. So if you don't like it, I'm sorry. But yeah, like that's how I call it. So we're going to talk about a story about the Python GIL. How many of you already know about the Python GIL? Yes, you know about it. How many of you really know what it is? Okay. The person is like now not very confident. So that's why you're here. I'm going to tell you a story about the GIL. And also, but first of all, okay, this is like a question that lots of people, when they meet, like, for example, your colleague who doesn't write Python, you may have an argument with them and say like, okay, we love Python. Python is awesome. But then someone will be like, but Python is slow, right? So, okay, so this is a scale. So because it's not a very good argument if you just say Python is slow, right? But how slow is slow? So, okay, it's just a gut feeling right now. There's no right or wrong answer. But so, we start with 0 because we're Python, right? So 0 is the slowest and then 4 is the fastest. So who think Python is 0? Slow, very, very slow. Okay, so already it's a good start. Okay, how about 1? It's kind of slow. Okay, more people. And then it's like, it's okay. It's like 2, which is like, normal. Some of you nod your head. Okay, what about 3? It's like, no, Python is actually quite fast. It's okay. I love it. Okay, what about Python is really fast? Yeah. Okay, none of you think Python is fast. No, we kind of know how it is, right? Like Python is an okay language. We love it, but Python is slow. But okay, this is actually a trick question because when we talk about Python is slow, we think about Python's performance is slow, but Python is actually fast in terms of when you have to put some ideas into code, right? You don't have to really like learn and think too much about pointers and all this like memory allocation when you're writing Python. So in that kind of sense, Python is actually very fast. So a lot of people, when we talk about Python, like the performance is really slow. A lot of people will talk about, the GIL. Usually we blame it for why Python is slow. But it's, again, like to really understand what we are talking about, we have to understand how Python works when we are doing some task, which is concurrency. So because I found that concurrency is a very weird concept. People have really, misunderstanding about it and what is concurrency. People are just like, oh, concurrency is just like doing multiple things at the same time, right? Not so simple. So let's look into it. So if you look online, right, like, oh, what is concurrency? You ask ChatGPT or, nowadays everybody, you just ask ChatGPT for everything, right? What am I going to eat today? ChatGPT can answer. So, yeah. But if you try to find the answer, probably you will get this answer similar to this one, which means that like, oh, concurrency, we are doing multiple tasks seemingly at the same time. So the key word here is seemingly, right? So sometimes we think, oh, concurrency means that we are doing the same thing exactly at the same time. But sometimes that's an illusion. You think your computer is doing 2 things at the same time, but actually it's not. If you really like pinpoint a certain moment in time, right? If you have superpower, you can freeze time, and you look at your computer, and it's actually not really doing multiple things at the same time. But it's just that because it's so fast, you think that your computer is doing multiple things at the same time. This is super weird. So usually, why we really, really like concurrency, why we want to have concurrency is that we have some issues with our code. So you may have heard about these terms like I/O bound and CPU bound. So what does that mean? So when you have your code or your application, so it's working, right? But sometimes it needs to stop because it is waiting for something to happen to continue. So it's just like, when you order some food, right? I really like eating, so I keep using food as an analogy. So if you order some food, right, you can't just like eat right after you order. You have to wait for your food to be, to come to your table, to, you get the food. So you have to wait. Even though you're really hungry, you really want to eat, but you have to wait. So that's kind of like an I/O bound problem. So I/O bound, I/O means like input and output. So what does it mean? Is that, for example, let's say you have some API call. So you are actually waiting for a result from an external process or external, API call, you're waiting for the server for response, right? Let's say. So that's the I/O bound problem. Or, for example, you are having, even if you're running something like a command line, application, you're waiting for the user to type in some input. That's also I/O bound. So sometimes your program needs to stop and wait. So if that happens a lot, let's say you're writing a client, you have to make a lot of API calls, or a lot of times the program need to slow down and wait for the response to come back. So then we will say that, oh, your application is very heavy I/O bound, okay, so you fall into that like red circle there. Another issue you have is CPU bound, which is this spinning square here. So CPU bound usually just mean something that really needs a lot of CPU power, as the name suggested. So it includes, for example, if you are handling a lot of data, especially data scientists, we know a lot of times when we train a model, there's lots of mathematical calculation. So those things are heavily like CPU bound because you need a lot of computing power to do some calculation. So it's actually not because of external you have to wait. It's because you actually need to do a lot of calculation. Well, because computer is number, right? So any calculation is, that's what computer do. So yeah, so that's CPU heavy, so CPU bound. So yeah, I've just like go through all of those. I should have gone to this slides, but anyway. So yeah, so you have two types of problem. So you have, like I said, the I/O bound balls, the red balls. The problem is that like, yeah, you have to read a lot of file as well. That's also like external. If you think about the process itself, it's external because then it need to ask the OS to like give me the file system, read that for me. That's also I/O bound. So CPU bound, like I said, it needs to handle a lot of information. Need to do a lot of computing power to do it. So happens a lot when you're a data scientist. Most of them are CPU bound processes. But the funny thing is like, a lot of people who do like machine learning, AI, and data science, they are using Python. So, which you will see later that like Python is not very good at speeding up CPU bound processes. So, but those two types of things that are slow, we can overcome it with different strategy. So for example, if your program is slow because of the I/O bound, because you have to wait a lot of times. So we are very good at that, right? Like I don't know if it's a Hong Kong thing or Asian thing. Like we are very good at doing basically async I/O in our daily life. So when we are waiting for something, we will just go to do something else. Like I just don't want to waste any time. Like that happens a lot when I'm cooking. So the first thing I do when I'm making a meal is to put the rice in the rice cooker, right? Because I have to wait, and I'm not going to watch the rice cooker cook the rice, right? And then I go to fry some dishes and do things, What happened here? Oh, why is it offline? You should not be offline. Okay. Anyway, let's continue. If something happened, we'll fix it. Okay. So yeah, like when you're waiting for the rice to cook, you are not just looking at it, right? You just do something else. You fry, fry some chicken or whatever you're doing. So yeah, so that's kind of what happened when we use async IO, or even threading in Python with GIL. So we'll come to that later, but so that is not a real concurrency. So that's not really something like your computer is doing multiple things at the same time. That's only when you are just using the waiting time to do something else. So you're juggling between two tasks. You are not actually like cooking the rice and cooking your dish at the same time. You're actually, because the rice is waiting, you're cooking your dish. So it's, we call it apparent or appear concurrent. Is because, technically it's not doing two things at the same time. It's just that, it goes back and forth. So it feels like it's doing two things at the same time. Threading is a bit tricky because we are now talking about the GIL. So we'll see how the GIL come into the picture in a bit. But with the GIL, threading is not true concurrent in Python. It's actually apparent concurrent as well. So you would be like, oh, so async IO and threading are the same, right? So kind of, but not really. That would be another talk about what's the difference between async IO and threading. So, but in short, async IO is passing the driving wheels between different, we call it a coroutine. So different, coroutine or actually async function. You think of it, they're passing the control around. But for threading, it's actually there's like a manager in your operating system to say, okay, now you can do that, or now you can do that. But anyway, let's not go too deep into that. That's IO bound. So CPU bound, so you have a lot of computation to do. So in Python, if we are talking about now is the standard Python, which is with the GIL, the only way you can do true concurrency is to use multiprocessing. But there's also like some drawback about multiprocessing. Multiprocessing is like you will have, like the name suggests, multiple Python processes happening at the same time. So each Python processes will have its own GIL. So technically, you are actually doing it at the same time because you're running multiple Python processes at the same time. But it comes with its own issue. For example, if you're sharing some data, then like any true concurrency programming, they will have some issues like, for example, race condition. You may have heard about that a lot. Garbage collection, reference counting, all these things, all this issue that Python kind of take care of it for you. Now it come back up because, you are trying to sidestepping the GIL, which is protecting you from all these issues. And now you're like, we don't need your protection. We'll deal with the issues ourselves. Yay. So that's how multiprocessing work. So that's how you can take care of CPU bound. Of course, if you're a data scientist or you're into like HPC, which is high performance computing, then, maybe we have a cluster and, again, let's not dive into it because we don't have enough time. So, okay, so we talk about all these like different issues that we are facing and how we're gonna, use different strategy to overcome those issues. But what's the GIL role in all these things, right? And actually, what is the GIL? What is it? So, GIL actually is not a real word. It's just, the Global Interpertor Lock. We just take the first letter of each of them. So like GIL, Global Interpertor Lock. But it's just a very fancy term for something that you may have already know, which is mutex. So in other programming languages, I code Rust sometimes. So Rust have this mutex. I'm pretty sure maybe C also have it, mutex, which is mutual exclusion. It means that you can't access and change some data at the same time by multiple threads. So sometimes it's called a lock. So that's why, Global Interpreter Lock, because it's kind of like a box holding some data inside, and whoever have the key can open it and, do something about the data, but not all of you all at once. Only one process with the key can do that, or one thread who have the key can do that. So this is a kind of a way to protect the data to, for race condition or anything that can potentially give you issues when you're running a program. So Python used this, super mutex, which is called GIL, in itself. So but why? Why do we have this? Because now everybody hate it. Why we have it in the first place? Well, because Python is actually quite an old language. So Python is actually, invented sometime. If you watch, there's actually the Python documentary right now. Watch that. It's really fun. But what I want to say is that in the 90s, when Python was created, at that time, we don't think about, okay, what if we have multiple core, we have multiple CPU, and, because at that time, like most computer at home only have one core. So, unless you work for some super, maybe some research facility, then it's not a problem. So the easiest way is to just use a giant mutex to lock everything in the Python itself. So, so the Python interpretation, when you write a Python interpreter, for example, CPython, it's very easy. It's very straightforward. A lot of things become less complicated because you can make the assumption that everything is locked. Everything will be only accessed by one thread at a time. So, so at that time, it's easy to write, easy to maintain, and straightforward. So that makes Python great. And we don't worry about multiple core at that time. But time flies and technology advanced. And now, even my computer here is not the newest, right? It's like, already 3-4 years old. This laptop have like 8 core. So, multiple core is kind of a standard right now. Like even a laptop will have multiple core. Like even your phone may have multiple core as well. So, now people are like yawning for, we want Python faster. We want Python to be able to do true concurrency, because, we want to optimize the performance. We want Python to be more useful in more applications. So, that's what the community wants, because Python is not a fun scripting language anymore. Python is used professionally in many companies and also driving all this machine learning and AI development. So we want Python to be faster. So, so now we have very, very good news, because after years of the, community, there are different heroes in the community trying to remove the GIL and have proposed a lot of methods. And now finally it become true. Python 3.13, which is already, out, is the, newest, released Python version today. There is a way to run it without the GIL, which is called three-threaded mode. They are basically the same thing, but sometimes I refer it as three-threaded Python, sometimes I refer with no-GIL Python, but they are actually the same thing. Very important note, because it's the first time that it has allowed someone, the users, to compile to build CPython with this like three-threaded mode is experimental, which is like kind of putting, a disclaimer saying like, it's not perfect yet, so be patient. Feel free to try it. If you have any problem, you encounter anything, you can, start doing what we do all the time in open source, issues and, report any concerns and, discussion within the community. So, but you can try it today, which is amazing. And it's the first step towards removing the GILs completely for Python. But it's not easy. I've said that before. Throughout the years, there are many, many, many heroes. Like they are super smart people in Python. They try to remove the GIL. but it doesn't come up with a solution that the community all agree that's, oh, let's do it that way. So it takes time. Sometimes it's because, the community need to adopt and, but now is the time. So in PEP 703 is a proposal is by Sam, and he proposed something, and then, Lucas sponsored that PEP, 703. So now this is, this is what the PEP 703 is talking about. I'm just going to, you can read it if you have time and want to know more, but I'm just going to give you a short summary of what's the most interesting bit that I found the most interesting about that PEP, and what challenges actually we are facing when we think about removing the GIL for Python. So, there are 4 sections. This 4th thing I found super interesting: reference counting, garbage collection, memory allocation, and compatibility. First, reference counting. Like I said before, with the GIL, right, we can make assumptions and, assume a lot of things just work because there's no race condition, there's no accessing the data at the same point. But now, if you remove the convenient GIL, then reference counting become a more complicated issue. So before, when we have the GIL, right, we would use non-atomic reference counting, which is the fastest way to do reference counting, which means that, you just do it straightforwardly, assume, assume no race condition and things like that. But if you don't have that guarantee, if you have to do it properly, you have to do atomic reference counting, which kind of takes time, right? So it's actually, maybe it's trying to make Python faster, but actually make Python slower. So the solution is to kind of find a compromise between the two. Something that is proposed is use a bias reference counting, which means that because Sam discovered that a lot of Python object actually is mostly accessed by one thread at, all the time. So if, an object have an owner's thread, then that owner's thread can just carry out non-atomic reference counting, which other threads need to do atomic reference counting. So the thread that owns it and accesses it the most actually can do it, can have a fast pass, speedy pass, and privilege, and don't have to do all these things properly, which others have to. So yeah, it's kind of a compromise, which is good. Garbage collection become way more complicated without the GIL, because, again, so with the GIL, when you have no reference count to an object, then you're very confident that it's not needed anymore. So you can just, remove it. But without the GIL, so now sometimes, when you update a reference, it can, again, who come first can actually create some funny situation. So that's why a technique called defer reference counting need to be used to double check. So when you remove a reference or something, is it really, really removed? You have to kind of check it, more thorough check to be sure that the object can be removed. So it won't be removed too soon. So other people are, I'm still using it. Why are you taking it away? So yeah, that's bad. So that's why we need that. Memory allocation. So before, when we, with the GIL, Python has its own memory allocator within its own Python process. So that's PyMelLog. But because we are now removing the GIL, PyMelLog is actually relying on the GIL, so we can't use that anymore. So a new memory allocator is needed for Python internally. So the new allocator that was proposed is actually not specific for Python. It's called PyMelLog. I think it's created by someone, I forgot the name, but later maintained by Microsoft, I think. So yeah, so it's quite a good one. Again, I don't go into the detail, but it's kind of suitable to use for Python because with some extra constraint, then you can have very fast access, which you don't have to do a lot of check to access the list and dig in Python, which people use a lot in Python. The last thing, compatibility. So we all know there's a lot of Python libraries are actually not written in Python. They are written in other languages and they got compiled into binaries. So that includes some, for example, NumPy, we love it a lot, it's actually written in C. So yeah, and all these like new fun stuff like Polars is written in Rust. So all these, you know, extensions, or called C API extensions because they are binaries, and then, you know, they are, you know, using the CPython API to kind of make Python can use a compiled binary code. That's magic. But there are other talks to talk about that, so I won't go into the detail. So for those, because now, you know, we change a lot in the Python itself, the GIL is removed. So for those, you know, let's say you are the maintainer of NumPy, you probably have to rebuild a version that's specifically for the free-threaded version, you know, for your users. Also, if your library have C extension, and when you designed it, you assume that the GIL is always there. It's not the case anymore. You may have to rewrite some code for your library. Yeah, and also now there's some restrictions as well, extra restrictions. For example, Python objects need to be allocated through the standard APIs. So yeah, so there are extra things. So this mainly affects people who are maintaining those you know, libraries with C extensions. But also if you're a user, right, if the maintainers are not updating it, then you really can't use something that is three-threaded ready. I know someone is doing a, someone called Nathan, I forgot his surname, but there's a project that is like checking all the popular Python library, are they three-threaded ready? So not all of them are ready right now. So yeah, if you want to help, please consider contributing to open source, yay. Last, okay, we would like to see if this free-threaded Python version is actually faster. So there's a little fun experiment that I've run. So for the code, you can actually, there's a blog post I've written in the PyCharm blog, actually is about this, you know, similar things. So this is one of the experiments that I do for the blog. So if you want to know the code, know the detail, you can go there and see. So it's the same script that is quite a computational heavy script, and run it with the standard version with the GIL. And so it's trying to do it with just one thread. So you can see the performance at the end here. So one thread is, you know, that's the baseline. And then we spin up and use multi-threaded, you know, version of, you know, just it's multi-threaded version of the code, which is like the same thing, but, you know, we do it throughout 4 threads. It's actually slower because when we do multi-threading, there's actually an overhead. So yeah, with the GIL, it doesn't help. It's actually make things worse. That's for a CPU-bound process. So if you have IO-bound process, that's actually can speed up, but we are testing it with only CPU-bound processes. So with no-GIL here, you can see it got speed up. So, you know, if you do mathematical calculation, it should be 4 times faster, right? But it's only 3.4 times faster, again, because there's an overhead. So, yeah, that's always you have to remember when you do multi-threading, even true concurrency will have overhead. So it won't be, you know, if you have 4 threads, it won't be 4 times faster. If you have 8 threads, it won't be 8 times faster. It's still slightly slower. So that's the end of my talk. Sorry I don't have time for Q&A, but you can contact me via all this, and I'll be also walking around at the conference. So yeah, feel free to contact me. And again, like if you have anything about PyCharm, you want to talk to me, please come and talk to me. So that's it. Thank you so much.